Welcome back, physics enthusiasts. I'm Swati, and in this video, we are going to do some important derivation from chapter 2, that is electrostatic potential capacitance. The video is going to be very interesting, very important for your last time revision for 2025 CBSE physics board exam. So all the important derivations and every stuff from chapter 2, which could be important for you, will be covered in this lecture. So let's begin with that. Okay, students. So the first topic would be electric potential due to a point charge. Though this electrostatic electric potential due to a single positive point charge. This particular derivation is not that important, okay, but I will teach you. You must know and just know the basics. Okay, so it's very easy. We have to calculate the potential. Now I'll give you basically the itinerary, the path which you should remember in your mind ki okay, this is how we have to follow to derive this equation, and the rest will follow automatically. Okay, the things which you have to remember is that you have to calculate potential. Potential can be calculated from work done, and for the work done you need force. So basically you need force, then we calculate work done, and we then calculate the potential. So this is how you have. So see, study smart. You must know what to remember. Okay, the rest will follow automatically. So for this, we have considered a positive point charge plus Q. Okay, whose potential we need to calculate. So consider a positive point charge Q, and at a distance of R, consider another test charge Q naught, positive test charge Q naught, and we have to calculate the potential from bringing it from infinity to a point in this in the field, in the space of this plus Q charge at a distance R. Okay, so now consider a positive point. Consider a positive point charge. Okay, and at a distance R, there is a positive test charge Q naught, which has come from infinity to a point in a space of plus Q. Okay, which come from infinity to a point in the space of plus Q charge, okay, at a distance x. Now first consider it as x. Okay, now this Q naught charge is then moved to some point A, which is at a distance of R. Okay, and since it's moved from P to Q, it has covered some distance, let's say dx. So first we cover the force between plus Q charge and Q naught. Yeah, you can also say the force exerted by plus Q charge on Q naught is as per the Coulomb's law, F is equals to K Q naught. We'll take only the magnitude upon x square, because initially it at x. Okay, now the work done. In moving the test charge, Q naught from infinity to a point R mein. Yeah, first consider small work done. The work done in moving the test charge Q naught at a distance dx. We have moved it through a very small distance dx. So for that, the work done would be force into dx, F dot dx. let's say that work is small because it has moved to a small distance. So dw is equals to f dot dx, which is f dx cos theta. And here you can see the force, because it's a positive charge, both are positive, the force will be in this direction, the displacement is in opposite direction, so theta would be obviously 180 degree. So the work done as theta is 180 degree, so your small work done is equals to minus f dx. Just substitute the value of force here, that is k q naught over x square dx. Fine. And total work done in moving the test charge q naught from infinity to a distance r from source charge would be total work done, which is the integration of dw, which is the integration from infinity to a distance r, k q naught by x square, dx by x square. So your total work done is basically k q naught is a constant, 1 by x square dx, integrate that term and we'll get 1 by x. S is raised to the power minus 2 plus 1 upon minus 2 plus 1. So it will be minus 1 by x from limit minus infinity to r, and we have a negative sign already there. So the one negative is there, then it would be k q naught 1 by r final minus 1 by infinity initial. This term is 0, 1 by infinity is 0. So the work done would be k q naught by r. Now the potential difference, we have to calculate the potential basically at a point r from this source charge would be final minus initial, that is potential at a distance r minus potential at infinity, final minus initial, is equals to work done into test charge q naught. Now the potential at infinity is considered as 0, it's a reference point, so potential at distance r from the source charge, which is a function of r, comes out to be upon q naught, this is upon q naught, comes out to be k q by r. Okay, so this is the formula of potential due to a point charge at a distance of r from it. Potential due to point charge, due to the point charge q से. Okay, fine. You must know the thing, it's not that important, इतना नहीं पूछा जाता, but you must know the basic thing. Okay, so the next one is potential due to dipole. Dipole is important everywhere. So for the electric dipole, I will explain you how to calculate the electric potential at a general point r, and then we'll calculate at x0 and equatorial point, which is very easy to calculate. Since potential is a scalar quantity, it's far more easy to calculate than the electric field, because here we have to consider the direction, but there in potential there is no direction, nothing. So it's simple scalar quantity, you have to plus minus considering the sign of the charge. So electric potential due to electric dipole at any generalized point, at any generalized point. Okay, so here we have considered again a dipole of charge plus minus q separated by a distance, of 2a. Okay, and electric field at point P at a distance of r, at a distance r from its center at an angle of theta, at an angle of theta. That is, now you can show the diagram that what do you mean by this is minus q, this is plus q. Okay, now from its midpoint, this is a midpoint. Yeah, this is a midpoint. From the midpoint, consider a point P here at a distance of r vector, making an angle of theta with what? With your dipole moment. Let this take this as P cap from negative to positive. Now consider that this point P is at a distance of r1 from minus q and a distance of r2. Okay, and if you need to calculate the difference, okay, before that just say simply the net potential at a point P due to both the charges. What it would be, potential at P is due to minus q charge, is due to plus q charge. Since it's a potential, you have to consider the sign as well. So with the minus q, we have calculated the potential due to single point charge as kq by r. So here it would be kq with a minus sign because it is minus q, and the distance here is r1. Okay, so it's simply r1 plus kq by r2. Kq is common in both the terms, take it out, minus 1 by r1 plus 1 by r2, then it is like kq r1 r2. This comes out to be basically r1 minus r2, because here it is minus r2 if you take the LCM, and here is plus r1, so it's r1 minus r2. Now as per the diagram, we have to calculate r1 minus r2. Since r1 is bigger, so you have to just divide the path, and this is r1 minus r2. Okay, now after this we have to consider one condition, or we can put a condition. So let's consider that r1 is almost equal to r2 is almost equal to r. That means this P point is somewhere very very close to the center point. That means all these three lines are not aligned like this, they are more parallel to each other. If they are more parallel to each other, means if they are more equal to each other, and this r1 is parallel to r2 is parallel to r, okay, if it is like this, then you can consider that this angle is also theta as per the corresponding angles, and this whole length is 2a, that is the length of the dipole. And from the geometry and the condition, and let's not take as condition, let's assume, okay, so from the geometry and the assumption, we can say that this r2 minus r1, if you look at this, it would be something like this. This angle is theta, this is theta. So now if this is theta, this is r1 minus r2, sorry, this is 90 degree, this is theta, and this would be 2a. This is base, this is perpendicular, so your cos theta, you can simply make a figure here. If this is theta, this is r1 minus r2, and this is 2a, this is some 90 degree angle, then you can simply say that cos theta is equals to base upon hypotenuse, and this r1 minus r2 is equals to 2a cos theta. So first you get this r1 minus r2, then for r1 and r2, since we first And for the second, since R1 is almost equal to R2 is almost equal to R, then R1 into R2 is equals to R into R, that is R square. Fine. So you can substitute this 1 and 2, or we can take as 2 and 3 in equation 1. Okay. So put equation second and third in equation 1. What you will get, that your potential Vp, potential at P is equals to KQ R1 minus R2, which is 2a cos theta over R1 R2, which is R square. Okay. And from here, Q into 2a is equals to P vector, that is dipole moment, and that comes out to be Kp cos theta by R square, which is a generalized formula. And one more thing, if you, its potential, there is no direction, but if you just multiply R and R above, upper and below, Vp R cos theta by R cube, then this PR cos theta is a scalar quantity, and you can write it as K P dot R vector over magnitude of R cube. So the dot product of two vectors will give you a scalar quantity. Fine. And for that, we have now two different things. One, at axial point, you can simply calculate from here also and from the derivation also. If you have derived a generalized formula, and after then you have to write its value of potential at axial and equatorial point. So you can, at axial point, you can simply put theta to be 0 degree, and your Vp comes out to be what? From here, Kp by R square, same like this. Okay. And if we talk about derivation part, so again, consider a dipole of charge plus minus q separated by 2a distance. Okay. Now, it's very easy. It's plus q, again minus q, and we have a point P at a distance of r from its center. So consider a point P where potential needs to be calculated, where potential needs to be calculated, okay, at a distance r from center. At a distance r from center. Okay, now its length is 2a. So for the half, okay, I think this is something half. This length would be a. This length would be a, and here to here it is r minus a, and from here it is r plus a as per the geometry. So the net potential at point P, is basically is the simple scalar plus minus. So V at P is equals to, from the positive charge it is KQ over the distance r plus a, and for the minus charge it is minus, okay, it is not from here, it is from like here, from the minus q charge, r minus a. Okay, this whole term will gives you, this is r, this is a, so this is r plus a, and for the remaining part, this is a, this is r, so you have to subtract it. Simple maths. Next is minus kq upon r minus a. Again take rq out, simply take LCM, solve it, it's very easy. This is r square minus a square, then this is r minus a, this is minus r minus a. You can subtract these two terms. and then it is KQ minus 2A. Don't worry about minus sign, it would be covered. Okay, so the minus basically Q into 2A is P, which is dipole moment, and your potential at this comes out to be minus Kp by r square minus a square. Why there is minus sign? Because we have taken negative to be close to P. So the net potential obviously comes out to be negative. Now if we interchange it, make this as positive Q and this as minus Q, automatically the potential at P will become positive because the positive charge is more close to P. Okay, so you can write the negative here as minus Q charge is close to P. It's close to P. So it's a dominant negative charge. Rest it's fine. So as per the condition for short dipole, Vp is equals to minus Kp by r square. Simply we have to neglect a square. Fine. Next, second is at equatorial point. Equatorial is very easy. First, you can simply check from the formula, that is Vp is for the generalized formula, which is Vp cos theta by r square. And equatorial point theta is 90 degrees, so Vp comes out to be 0. That is very important. Okay, sorry. So for the derivative part, consider consider a dipole of charge plus minus Q separated by a distance 2a. Okay, and consider a point P at a distance r from its center. At a distance r from its center at its equatorial point. At its equatorial point. Okay, and for that we can draw a diagram. This is minus Q, take this as plus Q, whole distance is 2a, and from its center let's consider a point P at a distance r. Then this distance would be what? Under root of r square plus a square, and then this distance would also be what? Under root of r square plus a square. Okay, and for the potential at point, this is because this is A and this is A. So the net potential at point P is basically what? Is sum of both the potential due to both the charges. This is minus KQ. Distance would be what? R square plus A square under root, and plus KQ upon में r square plus a square under root. Both the terms are same. One is positive, negative, so total effect is 0. That means there is no potential on the equatorial point. Since there is no potential, there would be no work done happen if any charge moves along this equatorial point. So this is again a star point, that is no work done. Work is done. No work done on the charge. On the charge while moving it along the equatorial line, equatorial line of dipole. Okay, so just remember this thing, but it's equipotential surface, but it's equipotential surface with net potential to be 0. Also on equipotential surface there will be no net work done because the potential is same. Potential difference V final minus initial would be 0, so there would be no work done. Also in equatorial line of dipole, the work done is also 0. Next is basically the relation between electric field and dipole. Okay, now the next is we have done electric dipole 1, 2, and that was 3. And now we'll do the third basic is relation between electric field and potential. Field and potential. Though its formula, its concept is very important. Many numerical concept based questions could be framed out of this topic, and trust me, you will find you will find at least one question from this particular topic. So I would suggest that practice numericals, and especially that graph based numerical, some graph or some diagram is given, and as per that diagram, question you have to answer. The question is given and you have to answer it. So just practice that particular type of questions, and you can also just keep in mind its derivation, but I think as per the numerical this topic is more important. So the relation between electric field and potential, its derivation is very simple, very simple. The thing is we will calculate work done using two things. One, by using force formula, F dot dr gives you work done, and another is using potential, that the potential difference is equal to work done by charge, and then we equate both the work done and we'll get the relation between electric field and potential. So the plan is that now you have to write it. So consider again a positive point source charge, okay, and a test charge, and a positive test charge Q naught is placed in its space at a distance x. We don't need that, but okay, we are writing it. So consider you have a source charge Q, positive charge, and at certain distance x, you have a source charge Q naught. Now, in its field, in the field of this Q charge, this Q naught charge is moved towards Q. Okay, now the Q naught charge moves towards Q by distance of dx, by a distance of dx from point B to A, from point B to A. Okay, so now consider that this is placed at A and then it moves to some point B at a distance of dx. Fine. Now the work done. Initially, we'll calculate the force, because we need force to calculate work done. So now the force, this basically plus Q will applied force in this direction and it has moved to this direction. So now the force on charge Q naught in the electric field E of source charge Q. Okay, so you can also write here, consider positive test charge of electric field E. Okay, because we need that. We need electric field, so we are not using kq by r square. Here we are using just E. So then that force would be Q naught times E, and work done in moving it through dx distance, it is same as above. The only thing is we are using E here. So So that work done is equals to F dot dr, and it is moving against it. So it's F dr cos 180 degree, because the force is in this direction and we are moving it in opposite direction. So that work done is basically what? Minus Q naught E dr dx. We have used dx. You can use x, you can use r. It's up to you, whatever notations you are using. Okay, put it as first. Now, when it moves from A to B, consider the potential at A to be V, and the potential at B would increase because here the work is done against the force. So when the work is done against the force, potential increases always, right? You can understood by this example that the gravity is pulling downward, but when we move to some height, the potential increases, mgh, right? So the potential is basically the work done against the force. So here the potential increases by some small value dV. So here we can write, if we consider potential at point A, that is VA is equals to V, then the potential at point B would be V plus dV. Okay, potential increases as work is done against the force. You can write, or you can, if you have understood, then it's fine. Potential increases as work is done against force. Okay, so here that work done is basically equals to Q naught and final minus initial, that is VB minus VA, and that work done is equals to Q naught, VB is V plus dV minus V से V cancel, then it would be Q naught dV work done. Okay, put it as equation 2. Now equate first and second because both are work done. You can equate that, and that comes out to be minus Q naught E dx is equals to Q naught dV. Q naught cancel each other, and that E comes out to be minus dV by dx. That is the negative gradient of potential. That is the gradient of potential. Gradient means change of any physical quantity with respect to distance, and here that physical quantity is potential, and negative sign shows basically, very important thing, that the potential increases in the opposite direction of V. Okay, or we can say potential decreases in the direction of electric field. Important one. For example, this is a point charge, electric field is going this direction, there is 2 points P and Q. So in the direction of electric field, potential decreases, therefore P is at higher potential than Q. Okay, so here there is one numerical on this in NCERT. I think it's an example thing. Okay, now the next third part is, here you can also write it as like the integration thing, that is dV is equals to EDX with a minus sign, and you can integrate it. So both can be there. Next is basically electric potential energy or work done in assembling the charges in a system. That particular topic is not so much derivation based. It is more in a numericals. You must know the formula, which is K, Q1, Q2 by R. If they ask for a derivation, then also it's not the proper derivation. Basically, since the formula, you have to get the potential and you have to multiply it by charge, you will get the work done. So the same format you have to apply for 2 charge system, 3 charge system, and you will get the net work done in assembling the 2 charge or the 3 charge. Basically in assembling you will get a positive work done, and when you disassembled it, then it will be negative. So I don't think there is some derivation. All you need to know is the basic concept behind that. So the next one And also the equipotential surfaces are very important because their shape is important and the properties are very very important. Again, I'm very pretty sure that you will get one or two questions from out of that topic. Okay, so the potential one, for the potential thing, just focus more on numericals, on concepts rather than the derivations. But for the second topic, that is capacitance, you have to remember the derivation. So the next thing we are doing is capacitance. Okay. If you have any query, any doubt until now, you can comment below. I will help you out with that. Okay. So in the capacitance, the first, the capacitance is basically the capacity of a conductor to hold charge on its surface or to store energy between them in form of electrostatic potential energy. So basically, it's a storing device in a form of and it store energy in a form of electrostatic potential energy. Okay. So in this first, which is important, is parallel plate capacitor. Parallel plate capacitor. Okay, this derivation is important. Other is with the dielectric form, when the dielectric in between the capacitor. So these two are the most important one. So for the parallel plate capacitor, consider two conductors. Two conductors of area A, placed parallel to each other. Placed parallel to each other at a distance of d. At a distance of d. Okay, having surface charge density sigma. Surface charge densities sigma. Okay, so now consider two plates. surface charge density प्लस माइनस सिग्मा ले लेते हैं. ठीक है, प्लस माइनस सिग्मा. It has area A. Let's say it has a plus sigma. That means it is a positively charged. Now consider a second conductor of same area of cross section but of different surface charge density, that is minus sigma. They both are separated by a distance d. Okay, now there would be electric field between these two plates. There can be electric field here, but because of plus sigma it is outward, because of minus sigma outward, and sigma by 2 epsilon naught is the electric field which is independent of distance. We have discussed this in the last video. So here the total electric field is 0. Similarly, here also, because of negative charge, it points towards the negative. Positive, it points away the negative positive plate. And here also E net comes out to be 0. And between the two plates, because of plus, it would be out sigma by 2 epsilon naught, and because of negative it points towards it, which is also sigma by 2 epsilon naught. So in between you have electric field which is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is sigma by epsilon naught. Okay, so you can show this in a very neat diagram, and you can also write here as the electric field between the plates, between the parallel plates, is equals to sigma by epsilon naught, and the potential developed between the plates, potential developed between the plates, V is equals to ED, and we are simply considering the magnitude. Okay, we are only taking magnitude because negative signs over the direction. So then you can write as V is equals to sigma by epsilon naught into D, put it as equation 2. Okay, and next is, and see, to calculate the capacitance, C is equals to Q by V. We have to calculate Q, we have to calculate V. As simple as that. So next is total charge. The total charge of the plate. The capacitor is basically a combination of two parallel plates which are equally and oppositely charged. So we have to calculate the charge of any one plate, and that is equals to sigma into A. Both have area same, which is A. Both have same surface charge density, that is sigma. So total charge will be sigma into A, as simple as that. Okay. Then the capacitance of the parallel plate capacitor of the parallel plate capacitor. See, it is basically a 3 to 4 step derivation. Electric field, then from electric field calculate potential, then calculate charge, and then calculate C, which is Q by V. As per the formula, Q is sigma A, V is what? Sigma D by epsilon naught. So sigma D epsilon naught goes up, and that capacitance in vacuum comes out to be epsilon naught A by D. Very simple. In any other medium, then you have an extra kappa here, which we will see in the next derivation, that electric field, the value of capacitance in the presence of dielectric. Okay, so it's a very simple derivation. Okay, so the second is, okay, the next is capacitance of a parallel plate capacitor with a dielectric slab. Okay, partially filled with a dielectric slab. First we'll do with partially filled. Okay, partially filled means there is some space between the capacitor plate and the dielectric slab. Partially filled. Okay, so here again same thing. Consider two conducting plates. Two conducting plates of area A and surface charge density plus minus sigma, and surface charge densities plus minus sigma placed parallel to each other at a distance of D. Placed parallel to each other at a distance D. Okay, and a dielectric slab of dielectric constant kappa of thickness T is inserted between the two plates. Okay, so you have one conductor of area A having surface charge density as plus sigma. Then you have a second conductor having surface charge density as minus sigma, and both has area A separated by a distance D, and there is a slab. Okay, there is a slab, same area of cross section, something like this. Okay, of thickness T. Okay, now the electric field, basically first electric field is developed between plus sigma and this, which is this E naught. Fine. And then another electric field is developed in between the plate, which is basically the polarization will occur in such a way that the outward electric field, external electric field is E naught. Okay, so Because of this, the negative charge would be here, the positive charge would be here. And from plus to minus, there will be an electric field which is EP, polarized electric field. So the net electric field here would be E naught minus EP because it is dielectric. If it is a conducting slab, then EP is equals to E naught. That's a polarization occur till all the charges separated in a conductor. But it is not a conductor, it's a dielectric, so some charge will left, that E naught and EP are not equal, therefore the E would be there. There is some electric field inside the dielectric slab. Okay, so now external electric field, the external electric field between the plates, E is basically what? Sigma by epsilon naught, right? And you can say that sigma is equals to charge per unit area. Q जो है, और you can simply write it as sigma by epsilon naught. Consider this as first. And electric field between the dielectric, that electric field, let's take this as E naught and इसको E ले लेते हैं, consider this as E, then that E is what? Basically, there is a ratio that the external electric field upon the change in electric field in the dielectric slab is equals to kappa. That is E naught upon में E naught minus EP is equals to kappa. So from here, E can be written as E naught by kappa. E naught by kappa, which is E naught is sigma by epsilon naught. So it is like this. Second. So these are two electric field. One is outer, external, and this is inside the electric, in between the electrics. So the potential developed between the plates, V is equals to what? E naught with that distance, and the distance would be the remaining one, that is complete D minus T. Okay, the distance in which your E naught lies, and that is like only this and this one. And for that E electric field, the distance is T thickness. So plus E into T. Just put the value of E naught and E. E naught is sigma by epsilon naught, D minus T, and E is what? Sigma by kappa epsilon naught into T. Fine. Just put that as equation. Okay, first we can calculate sigma by epsilon naught to be common, D minus T plus T by kappa. Now just mark this as equation number 3. Okay, now charge on the plates, on the conducting plates, that Q is equals to what? Sigma times A. Let's put it as 4. Okay, so now the charge, now capacitance. Now the capacitance of the parallel plates are with the dielectric slab. C is equals to Q by V. Q is what? Sigma A. V is what? Sigma by epsilon naught. D minus T plus T by K. D minus T plus T by kappa. And this sigma cancel, then it is epsilon naught A upon D minus T plus T by kappa is the capacitance between the parallel plate capacitor in the presence of dielectric slab, which is partially filled. Now if it is fully filled, dielectric slab, then D is equals to T, because whatever the distance between the two plates is covered with dielectric slab having thickness T, so it comes out to be epsilon naught A. This just put T to be D, so D minus D plus D by kappa. Here you can cancel D, kappa goes up, and from here also you can say that if this is the capacitance in a vacuum, then the capacitance in any medium will become kappa times the capacitance in vacuum. You can also prove from here. Okay, so whatever be the dielectric slab, if dielectric slab is like conductor, so if dielectric slab is a conductor, so for the conductor kappa is infinity, so this term will goes to 0 and your C comes out to be very easily epsilon naught A d minus t. Basically you have to remove the space of that conducting slab or the thickness of that slab because it offers you nothing. So it becomes a epsilon naught d minus t. Basically this decreases. If the slab is conducting, then your capacitance will decrease. Okay. Okay, the last one is we'll calculate the energy density of a capacitor. Okay, the next is capacitance of a parallel plate capacitor with a dielectric slab. Okay, partially filled with a dielectric slab. First, we'll do with partially filled. Okay, partially filled means there is some space between the capacitor plate and the dielectric slab. Partially filled. Okay, so here again same thing. Consider two conducting plates. Two conducting plates of area A and surface charge density plus minus sigma and surface charge densities plus minus sigma placed parallel to each other at a distance of d. Placed parallel to each other at a distance d. Okay, and a dielectric slab or dielectric constant kappa of thickness t is inserted between the two plates. Okay, so you have one conductor of area A having surface charge density as plus sigma. Then you have a second conductor having surface charge density as minus sigma. Both has area A separated by a distance d, and there is a slab. Okay, there is a slab, same area of cross section. Something like this. Okay, of thickness T. Okay, now the electric field basically, first electric field is developed between plus sigma and this, which is this E naught. Fine. And then another electric field is developed in between the plate, which is basically the polarization will occur in such a way that the outward electric field, external electric field is E naught. Okay, so because of this, the negative charge would be here, the positive charge would be here. And from plus to minus, there will be an electric field which is EP, polarized electric field. So the net electric field here would be E naught minus EP because it is dielectric. If it is a conducting slab, then EP is equals to E naught. That's a polarization occurred till all the charges separated. in a conductor, but it is not a conductor, it's a dielectric. So some charge will left, that E naught and EP are not equal, therefore the E would be there. There is some electric field inside the dielectric slab. Okay, so now external electric field, the external electric field between the plates, between the plates, E is basically what? Sigma by epsilon naught, right? And you can say that sigma is equals to charge per unit area. Q जो है, और you can simply write it as sigma by epsilon naught. Consider this as first, and electric field between the dielectric, that electric field, let's take this as E naught and इसको E ले लेते हैं, consider this as E, then that E is what? Basically, there is a ratio that the external electric field upon the change in electric field in the dielectric slab is equals to kappa. That is E naught upon me E naught minus EP is equals to kappa. So from here, E can be written as E naught by kappa. E naught by kappa, which is E naught is sigma by epsilon naught. So it is like this. Second. So these are two electric field. One is outer, external, and this is inside the electric, in between the electrics. So the potential developed between the plates, V is equals to what? E naught with that distance, and the distance would be the remaining one, that is complete D minus T. Okay, the distance in which your E naught lies, and that is like only this and this one. And for that E electric field, the distance is T thickness. So plus E into T. Just put the value of E naught and E. E naught is sigma by epsilon naught, D minus T, and E is what? Sigma by kappa epsilon naught into T. Fine. Just put that as equation. Okay, first we can calculate sigma by epsilon naught to be common, D minus T plus T by kappa. Now just mark this as equation number 3. Okay, now charge on the plates, on the conducting plates, that Q is equals to what? Sigma times A. Let's put it as 4. Okay, so now the charge, now capacitance. Now the capacitance of the plates, parallel plates are with the dielectric slab. C is equals to Q by V. Q is what? Sigma A. V is what? Sigma by epsilon naught. D minus T plus T by K. D minus T plus T by kappa. And this sigma cancel, then it is epsilon naught A upon D minus T plus T by kappa is the capacitance between the parallel plate capacitor in the presence of dielectric slab, which is partially filled. Now if it is fully filled, dielectric slab, then D is equals to T, because whatever the distance between the two plates is covered with dielectric slab having thickness T, so it comes out to be epsilon naught A. This just put T to be D, so D minus D plus D by kappa. Here you can cancel D, kappa goes up, and from here also you can say that if this is the capacitance in a vacuum, then the capacitance in any medium will become kappa times the capacitance in vacuum. You can also prove from here. Okay, so whatever be the dielectric slab, if dielectric slab is like conductor, so if dielectric slab is a conductor, so for the conductor kappa is infinity. So this term will goes to 0 and your C comes out to be very easily epsilon naught A d minus t. Basically, you have to remove the space of that conducting slab or the thickness of that slab because it offers you nothing. So it becomes a epsilon naught d minus t. Okay, so the next is third one. What is it? Third one. Okay, in the capacitor part. Third is energy density. Again, this is important. Since there is no derivation on energy, the energy formula, which is how CV square, that part, there is for that part, there is no derivation, but you can check the energy density. Okay, it's very easy again. So for the energy density, first consider again a parallel plate of this. So I'm just skipping that part. Okay. So if this is a capacitor, I'm not writing it, I'm just making a diagram having surface density plus minus sigma separated by distance d, area of cross section to be A, then you can write as the electric field. Basically you energy density. So energy is half CV square or half Q square by C. Okay, and there's one more formula. So I'm using this half Q square by C for parallel plate capacitor. All you need to do is to find Q and C and just substitute it. Okay, so first is the electric field between the plates is E is equals to sigma by epsilon naught. You know that. And sigma is equals to E epsilon naught. This is first. So therefore, next we have to calculate the charge. So the charge on the plates Q is equals to what? Sigma times area, and that sigma comes out to be E epsilon naught. You must know the formula. The formula is half epsilon naught E square. So just go by like that key E should be there. So that's why I start with E. And next you have to calculate C. The capacitance of the parallel plate capacitor of the parallel plate capacitor C is A epsilon naught by D. Okay? Put that as equation 3. Now the energy stored in the capacitor is U, which is half Q square by C. Okay, now just put the value of 2 and 3 here. Your energy comes out to be half Q square is the square, which is E square epsilon naught square A square over C, which is A epsilon naught by D. A epsilon naught, but just put the D there. You can cut the squares and that U come out to be half epsilon naught E square into AD. Okay, where area into distance is basically the volume between the plates, right? Area into distance between the two plates, and if you bring that AD down, then this become energy per unit volume, epsilon naught E square, and this is basically what? Energy per unit volume, and you can write as U, which is energy density small u, which is equals to half epsilon naught E square. So you can see that all the derivation is following the same format for capacitance. Okay. The derivation of energy half CV square is not there in the course. Now, even for the series and parallel combination, I don't think that derivation is that important because if they want to ask, they will give you the numericals. So this much. for the chapter number 2, इलेक्ट्रिक पोटेंशियल कैपेसिटेंस में कैपेसिटेंस अच्छे से कर लेना, एंड जो छोटे मोटे जो भी सारे तुम्हारे कॉन्सेप्ट्स हैं उनको अच्छे से पढ़ लेना. एंड नेक्स्ट अपन करते हैं करंट इलेक्ट्रिसिटी पे. सो थैंक यू फॉर वॉचिंग दिस वीडियो, एंड डू लाइक, सब्सक्राइब एंड शेयर, एंड notify yourself, जैसे कोई भी आगे नया वीडियो आए तो तुम्हें पता चलता जाए. सो हिट द बेल आइकन. आई एम लर्निंग ऑल द यूट्यूब टर्म्स. एनीवेज, thank you again, and just revise karo, and if you have any problem, any doubt, you can comment below. I will help you out with that.